Hello, today I'd like to talk about my final project, Distributed Key Value Store with Raft Consensus Algorithm. And here's the agenda. I would like to first talk about the motivation behind choosing this topic, and then, since this project is built on top of our assignment, I would like to talk about some relevant information and talk about the implementation of my Raft Consensus Algorithm, mainly focused on request vault RPC and append log RPC, and show a simple experiment that I conducted to understand the latency of the program. And lastly, further optimization that I could have done for this program. And for the motivation, I don't know how everyone felt, but reading Raft paper wasn't as challenging as other system papers that we had to read for our assignment. Or is it going to be not as difficult to implement as well as a developer? That was the question I want to answer. And the short answer to my experience is it is difficult. It was quite challenging to me due to various corner cases that I had to consider. Um, and next reason is straightforward. I want to improve concurrency and C++ programming skills, as well as have a better understanding of the algorithm that is underlying various modern distributed systems such as etcd, which is an open source distributed key value store system that Kubernetes used for maintaining the state of clusters, RabbitMQ, MongoDB, to just name a few. For a quick overview of our assignment, client programs support two types of requests, read and update requests. And for server, an original implementation, it included three threads, engineer thread, expert thread, and idle server thread. And to simplify implementation, I removed idle server thread in my ref program. Additionally, I've added timeout thread that allows multicasting specific RTC calls for every interval between 200 milliseconds to 300 milliseconds. Image on the left is the engineer thread that is created for every socket connection within the server. First thing it does is to identify sender, and once the sender is identified, the process is routed to each handlers. On the right is a server handler, and it is additional layer that I have added to route the connection to appropriate RPC call handler. On the left is the state machine included in the original paper, and the logic is clearly represented in the pseudocode of the timeout thread on the right. As most of you guys would remember, there are three states, follower, candidate, and leader in Raft, and each state has its own behaviors. Follower will wait for RPC calls, and if heartbeat is not received within a certain time, it promotes itself to candidate. Candidate will send request RPC, and based on the result, it will promote itself as the leader or demote as the follower. Leader sends append log RPC, and based on the communication, it may demote to the follower. Now with the request vote RPC, identifier of the request vote RPC is sent first, and then request vote RPC with the information on the right is sent. In order for the receiver to vote yes, candidate's current term has to be bigger than or equal to the receiver's. Additionally, the term of the last log at the candidate server has to be bigger, or if it is equal to the current server, there should be more log in the candidate in order for the server to vote for the candidate. Otherwise, it votes no. As the candidate collects the vote, if the current vote counts as the majority vote, it promotes itself as the leader. If the term is smaller than the voter's term, it demotes itself to the follower. Otherwise, split vote as it happened and stay as the candidate. The Panlog RPC implementation was quite challenging. To account for this server failure, I used Stack to store the failed nodes, and for every appendlog RPC, I tried reconnecting with the failed servers. Then the leader would send RPC identifier to route the receiving server to the appendlog RPC handler. As you can see on the right, leader stores an array of length of sent logs and length of the acknowledged logs for each follower servers. If the sent length of the node is the same as the log size of the leader, leader sends an empty append log. Otherwise, it sends a log information at the prefix length. Comparison with current term happens in append log as well as request full RPC. If the current term of the leader is bigger and the server is candidate, it demotes to follower, and then defines can log a Boolean value where it is true if log size of the recipient is as big as the request's prefix length and term of the previous log is the same. If there is more logs in the receiver, it drops uncommitted logs, and then it appends logs if it is not a heartbeat append log, and execute based on the commit length. For leader, it simply increase or decrease the value in the array by 1 until all the logs are sent to the follower. Now with some of the adjustments and assumptions I have made, heartbeat timeout interval is 1. I changed the range from recommended length 150 to 300 to 200 to 300 milliseconds. This was to account for the rare case where some follower were promoted to the candidate when there was a leader, even though the leader was constantly sending pen log heartbeat. And the problem was fixed once I extended the range. Next, when follower receives update request, as far as I remember correctly, the unprocessed order was sent from the follower to the leader in original Raft implementation. Instead, I made follower to communicate the server node information to the client and let client order again directly to the leader server for the performance. Next, for test conveniency, I used 3 nodes for test purpose instead of 5. And other two are assumptions I have made. I wasn't able to come up with the solution when leader dies during processing client requests. I wasn't able to answer to the question, how would the follower know whether the request was complete or not if it were to take over the client's request? Another assumption I had is that there is at least one server alive to make up for the fact persistent memory was not in place. Moving on to the experiment, as you can see, latency increased linearly with the increase of additional thread. Slope was around 160 milliseconds per thread, and I didn't expect latency to be this high until the very last day of the assignment due date. And I didn't have enough time to debug, but I do have some potential reason that comes up to my mind. Um, it could have been from removal of the worker thread, or it could have also been from inefficient synchronization. Quick fix would have been to batch the client order with some rule to keep the order of the client ID and order number across the servers. And I think latency would have decreased significantly with that. Adding to the client batching, there are lots of optimizations that could have been done. I feel like my code would have been more useful if it was designed more modular. And also, adding persistent memory for each server would have helped me relieve the assumption that at least one server has to live and which allows more robust system. And my program included pre-configured members through client line argument when starting the program, um, but including changing member configuration, which is something that is quite extensively discussed in the original paper, I think would have been more realistic. Last but not least, there are some edge cases that I have included in the code, but was not able to test, like the case of network partition. I felt like development might have been easier and thorough if there were, or if I had built a simulation model first. Moving on to the demo, you're seeing 4 terminals, and I'm going to use the first 3 terminal as a server and start calling them 71, 72, and 73. And I'll use the last terminal as a client. I'll start all 3 servers, and server 3 has been elected as the leader at current term 5. And I'll send a update request of size 1 to the leader, and log is appended and log requests were sent to server 71 and 72. Now I'll kill both servers, and the follower server failure should not break the leader program. Um, while the leader cannot commit, I'll send the update request from the client to the leader. And leader has appended two logs, and we're not expected that the log is committed. Um, we'll check this by sending a read request from the client. And as you can see, the last order has not been committed. Now I'll put the server back to life. And all the servers that came back to life should have logs recovered, and the uncommitted logs from the leader should be now committed as well. We'll send a read request to server 71, and the logs are recovered and the last order has been committed as well. Same with server 72 and server 73. Now I'll kill the leader and kill the another follower server as well. And killing leader server should not affect other programs. I'll put all the servers back to life. And this time I'll send the order from the client to server, this order size 1 to server 73, which is a follower server. And as you can see, the order has been processed by the leader server instead of where the order has been received and replicated from the leader to the follower.